Water quality can be determined by looking at the water's effect on public health, how close it is to the normal concentration, expected end use, and by the impact it has on the ecosystem. Water pollution is the contamination of bodies of water which leads to a decrease in the water quality. And right now, clean, disease-free drinking water is the largest concern globally. 1 in 10 people lack access to safe water, and every year 3.4 million people die of water-related diseases. Water pollutants include heavy metals, sediment, certain radioactive isotopes, heat, fecal coliform bacteria, phosphorus, nitrogen, sodium, and other useful, even necessary elements, as well as certain pathogenic bacteria and viruses. Most water pollution results from runoff and leaks, or seepage of pollutants into surface water or groundwater. Pollutants are also transported by air and deposited into bodies of water. Pollution can come from a point source or a non-point source. Point sources are distinct and confined sources like pipes emptying into streams or rivers. You can literally point to where the pollutant is coming from, making point source pollution easily identifiable. Non-point sources come from large areas like parking lots and agricultural runoff. The contaminant diffuses and it becomes more difficult to find the source of the pollution. Runoff is water that runs over the surface of land and collects all of the pollutants that were deposited on that surface. Pollutants in runoff can include nitrogen, phosphorus, fertilizers, pesticides and herbicides, silt, sediment, and soil, pathogens like E. coli and coliform bacteria, salmonella, and cryptosporidium, ammonia, and animal feces, salt, motor oil, grease, antifreeze, rubber, gasoline, trash, detergents, sulfuric and nitric acid from acid rain, and mercury from contaminated rainfall. It is difficult to monitor disease-carrying organisms directly. We use the count of fecal coliform bacteria as a standard measure and indicator of disease potential. The presence of fecal coliform bacteria in water indicates that fecal material from mammals or birds is present, so organisms that cause waterborne diseases may be present as well. The growth of the fecal bacteria will cause an increase in the biological oxygen demand. It is difficult to monitor disease-carrying organisms directly. We use the count of fecal coliform bacteria as a standard measure and indicator of disease potential. The presence of fecal coliform bacteria in water indicates the fecal material from mammals or birds is present, so organisms that cause waterborne diseases may be present as well. The growth of fecal coliform bacteria will cause an increase in biological oxygen demand. Two important nutrients that cause water pollution problems are phosphorus and nitrogen, and both are released from sources related to land use. Agriculture causes contamination when excess phosphorus and nitrogen are added to the surface or groundwater. The contamination is usually caused by runoff or fertilizer or animal waste. The amount of oxygen required for biochemical decomposition processes is called the biological or biochemical oxygen demand. BOD is commonly used in water quality management and testing. Dead organic matter, which produces BOD, enters streams and rivers from natural sources such as dead leaves from a forest, as well as from agricultural runoff and urban sewage. If sewage is dumped here, BOD increases. Dew drops due to the increase in microorganisms and bacteria decomposing in the organic matter. Eutrophication is when excess nitrogen and phosphorus cause algae in the water to grow excessively, also known as algal blooms. As the algae dies, the microorganism and bacteria that decompose the algae use up all of the accessible oxygen, which kills the other living organisms in the water since they don't have enough oxygen. Cultural eutrophication is anthropogenic addition of nutrients to a body of water. Basically, it's when humans' activity leads to the addition of nutrients to a body of water, causing eutrophication. Eutrophication then can cause algal blooms, lower levels of photosynthesis in the water column, increased levels of nutrient concentrations, and decrease in dissolved oxygen levels. Hypoxia is oxygen deficiency in a biotic environment. When there is not enough oxygen in a body of water, this zone becomes known as dead zone, since there isn't enough oxygen left to sustain life. The oxygen is depleted due to excess nutrients that cause eutrophication. The solution to cultural or artificial eutrophication involves ensuring that high concentrations of nutrients from human sources do not enter lakes and other bodies of water. This can be done by using phosphate-free detergents, controlling nitrogen-rich runoff from agricultural and urban lands, disposing of or reusing treated wastewater, and using more advanced water treatment methods, such as special filters and chemical treatments that remove more of the nutrients. When too much sediment enters a body of water, the water can become cloudy, preventing a sufficient amount of light to the aquatic plants, preventing them from growing. Sediment can also clog up fish's gills, prevent animals from being able to see food, and enough sediment buildup can alter the flow of water. By weight, it is the most abundant water pollutant. It can be minimized by trapping eroded sediment at construction sites, only exposing a minimum amount of land at a time, and considering the natural contours of the land during construction. Also, by providing protection to exposed soil during construction. Wetlands are naturally functioning water treatment and purifiers, meaning they naturally perform secondary and tertiary or advanced treatment. The water is not purified completely, but it is done free of charge. The principal advantage of using wetlands for wastewater treatment is that a natural ecosystem replaces industrial methods for secondary and advanced treatment. So water enters a wetland through streams or groundwater. As the surface water runs through the wetland, contaminants and sediments are filtered, resulting in a cleaner water outflow back into the stream. As the groundwater flows into the wetland, bacteria breaks down contaminants, and then the saturated peat stores the water, resulting in a slow release of the cleaner stored water. Beyond being a natural filter, wetlands are critical wildlife habitats as well. Wetlands are classified in 3 different ways. They can be classified by hydrology, since they will usually have standing water, by soil type, which is normally rich in organic matter, and by species composition. So the types of plants, animals, and microorganisms that occupy the area are usually riparian, meaning they're related to or situated on the banks of the river. There are ways to clean up surface and water pollution. The first way is by using nanotechnology, which uses extremely minute particles to help treat wastewater. The second way is using urban runoff naturalization. This is an emerging bioengineering technology to treat urban runoff before it reaches streams, lakes, or oceans. Groundwater pollution can come from sources like landfills, subsurface gasoline tanks, oil spills, and saltwater intrusion. Cleanup is a very expensive process. The soil can be removed and disposed of as hazardous waste, or treatment of the water can be performed using a process known as vapor extraction. Treatment may also use microorganisms that consume the gasoline. This is known as bioremediation and is much less expensive than removal, disposal, and vapor extraction. Pollution from leaking buried gasoline tanks emphasizes some important points about groundwater pollutants. Some pollutants, such as gasoline, are lighter than water and thus float on the groundwater. Some pollutants have multiple phases: liquid, vapor, and dissolved. Dissolved phases chemically combine with the groundwater. Example: salt dissolves into water. Saltwater intrusion is common in coastal areas where the groundwater can have saltwater intruding into the aquifer. This usually occurs when local water users remove more groundwater than is naturally replaced. In the diagram below, we can see that the irrigation well is removing fresh groundwater. As more of the fresh water is removed, the ocean water begins to fill in, causing the well closer to the ocean to become contaminated with salt water. Water is a very easy way for disease to be transmitted. Cholera in water is tested by looking at the coliform bacteria content. This is the most important concern for water treatment. Septic tanks treat wastewater in rural residences. They can be considered private sewage treatment plants. The sewer line from the house leads to an underground septic tank in the yard. The tank separates solids from liquids, digests biochemically change, and store organic matter through a period of detention. This allows the clarified liquid to discharge into the drain field from a piping system. The treated sewage seeps into the surrounding soil. It is further treated by natural processes of oxidation and filtering. By the time the water reaches any freshwater supply, it should be safe for other users. Wastewater treatment, or sewage treatment, costs about $20 billion per year in the United States and keeps rising. It is divided into 3 categories: primary treatment, secondary treatment, and advanced wastewater treatment, or tertiary treatment. Primary treatment is when solid debris is removed by screens and meshing. Many different processes are used to filter and allow sediment to settle. Sometimes a flocking agent is used to force some chemicals to precipitate, clump out, and settle. Secondary treatment is when organic material is consumed by bacteria which need oxygen to assist in removing the organic waste. Tertiary or advanced treatment is when the use of carbon filter, chlorination, UV ozone, etc. is used to sterilize and kill pathogen or other pathogenic organisms. Wastewater treatment is not used to drink because it is not designed to remove nitrogen, phosphorus, and pharmaceutical drugs from the wastewater. During primary treatment, pollutants like large objects, sand, grit, fecal matter, fats, oil, and grease are removed. To remove the solid screens, nets and filters are used. A settling tank is used to remove sand, grit, and fecal matter. The settling tank slows incoming water so that the materials can settle out. This is also called a deterrer or a sand catcher. Fats, oils, and grease can be mechanically skimmed off the top of the water. During secondary treatment, pollutants like dissolved and suspended organic substances, pathogens like bacteria and E. coli, phosphate, nitrates, and ammonia are removed. To remove the organic substances, effluent is brought in contact with oxygen and aerobic microorganisms that break down or consume the organic matter. Anaerobic microbes digest, and then secondary sedimentation and floc removal. Disinfection is used to remove pathogens. Lime, alum, aluminium sulfate, iron chloride, iron sulfate, and biological removal can be used for phosphate, and denitrifying bacteria removes nitrates and ammonia. Bioremediation is the use of bacteria to clean up a pollutant like an oil spill. The diagram below shows a method for remediating the contaminated soils in quantities of 1,000 years or more. After being placed in a ventilated biopile, soil is treated with a blend of selected chemicals and microorganisms that naturally break down the toxins into less harmful compounds. After treatment, the treated soils can be safely landfilled or taken off-site for other uses. Wastewater is being applied successfully to natural and constructed wetlands at a variety of locations. In Figure A, we see a photograph of a site showing wetlands integrated with housing development, and in Figure B, we see a map of the artificial wetlands for treating agricultural wastewater at Avondale, Arizona. In Las Vegas, Nevada, new resort hotels that use a great deal of water for fountains, rivers, canals, and lakes are required to treat wastewater and reuse it. Maintaining water quality is really important, and there are a lot of ways to treat drinking water. Adsorption is when contaminants stick to the surface of granular or powdered activated charcoal. Disinfection utilizes chlorine, chloramines, chlorine dioxide, ozone, and UV radiation. Filtration removes clays, silts, natural organic matter, and precipitation from the treatment process. Filtration clarifies water and enhances the effectiveness of disinfection. Flocculation removes sediment. This process combines small particles into large particles that then settle out of the water as sediment. Alum, iron salts, or synthetic organic polymers are generally used to promote coagulation. Ion exchange removes inorganic constituents. It can be used to remove arsenic, chromium, excess fluoride, nitrates, radium, and uranium. There are also many methods to cleaning groundwater. Enhanced bioremediation enhances the natural rate of bioremediation by adding oxygen and nutrients into the groundwater. Fluid vapor extraction applies a vacuum system to low permeable soil to remove liquids and gases. Granulated activated carbon, or GACs, is when groundwater is pumped through a series of columns containing activated carbon. Hot water or steam flushing forces steam or hot water into an aquifer to vaporize volatile contaminants and then is treated through fluid vapor extraction. In well air stripping injects air into wells, the air picks up various contaminants, particularly VQCs. Vapors are drawn off by vapor extraction. Ion exchange involves an exchange of one ion for another. Phytoremediation uses plants to remove contamination. UV oxidation uses ultraviolet light, ozone, or hydrogen peroxide to destroy microbiological contaminants.